Hello students, welcome to second lecture of biomolecules. In previous lecture we discussed about some basic introductory part and classification of carbohydrates. Now let's discuss further. In last lecture we discussed about classification of carbohydrates and we also discussed that they are also referred as saccharides. So simplest saccharides are referred as monosaccharides. So now let us discuss about some different type of examples of saccharides. So monosaccharides are further classified on the basis of number of carbon atoms and functional group present in them. If monosaccharide contains aldehyde group, then it is known as aldose, and if it contains ketone, then it will be known as ketose. And number of carbon atoms constituting the monosaccharide is also introduced as these names suggest. So as the example suggests, if you have 3 carbon atom, then triose word will be used, and if it contains aldehyde, then it will be aldotriose, and if it is ketone, then it will be ketotriose. Similarly, for 4 carbon containing compounds, tetrose word will be used, and if you have ketone, then it will be ketotetrose, and aldehyde, that means it will be aldotetrose, and so on. So naming schemes are mentioned here. So we can say that from the name we can identify number of carbons and functional group of given saccharide. That means suppose if name is aldohaptose, then we can say that it contains aldehyde group and 7 carbons. So our first monosaccharide and well-known example is glucose. Glucose occurs freely in nature as well as in combined form. It is present in sweet fruits and honey. Ripe grapes also contains glucose in large amount, and it is prepared as follow. So first method to prepare glucose in laboratory or in factories is as mentioned from sucrose or cane sugar. That means we can break the molecule of sucrose into glucose and fructose. As mentioned earlier, sucrose is a disaccharide consists of one glucose and one fructose molecule. So when sucrose is boiled with dilute HCl or H2SO4 in alcoholic solution, glucose and fructose are obtained in equal amount. Now HCl or H2SO4 will act as catalyst, and this catalyst will increase the rate of reaction. So simple reaction will be C12H22O11 with H2O. In presence of H plus gives C6H12O6 glucose and C6H12O6 fructose. So notice here glucose and fructose both have same type of molecular formula, but their structures are different, their functional groups are also different. So they are completely different molecules in nature, but they share same number of atoms. Second is from starch. So commercially glucose is obtained by hydrolysis of starch by boiling it with dilute H2SO4 at 393 Kelvin temperature under pressure. So starch or cellulose are actually, we can say that a polymer of glucose. Multiple glucose molecules are joined together to form starch or cellulose. So they contain C6H10O5 repeating units, and when it reacts with H2O, because of hydrolysis, it will produce glucose molecules. By this method we can obtain comparatively large amount of glucose and it will be pure. In previous method, that means when we separate out sucrose, you will get glucose and fructose in mixture form. So that means you have to separate them to obtain purified glucose. But in this method, pure glucose will be only product. So this is more convenient reaction. Large quantity and purified product. Now let's talk about the structure of glucose. That means with the step-by-step reaction, we will try to find which type of structure glucose have. Glucose is an aldohexose. So from the name we can say that it contains aldehyde group and 6 carbons. And it is also known as dextrose. It is the monomer of the many of the larger carbohydrates, namely starch, cellulose. It is probably the most abundant organic compound on earth. It was assigned the structure given below on the basis of following evidence. So here we have some evidence. So first of all, molecular formula was found to be C6H12O6. It is easy to find. Next, the prolonged heating with Hi, it forms N-hexane, suggesting that all of the 6 carbon atoms are linked in a straight chain. So simple reaction, when we heat something with Hi, when we heat carbonic compounds with Hi, you will get carbon chains as alkane. So if all of the carbons are not connected with each other, you will get smaller number containing hydrocarbon chains than the actual reactor. That means, let us say if 2 carbons are connected with each other, then we have oxygen between them and remaining 4 carbons are later. Then you will get 2 different molecules of alkane when we react them with Hi. One will be ethane, one will be butane, but in this case we get hexane that represents all of the 6 carbons present in the glucose are connected in a series. So from first point we derived that we have 6 carbons, 12 hydrogens and 6 oxygens to arrange in a structure of glucose. From second stage we can say that all of these 6 carbons are in straight chain, okay, and they are linked with each other. Third point, glucose react with hydroxyamine to form an oxime and add a molecule of hydrogen cyanide to give cyanohydrin. This reaction confirms the presence of carbonyl group, that means C double bond O group in the glucose. So as the name suggests, it is aldehyde, so that means obviously C double bond O group will be present. Similarly, if it is ketone, then still it also contains C double bond O group. So how can we confirm it? So here 2 different reactions are mentioned. When we react aldehyde with NH2OH or C double bond O group with NH2OH, it gives us NOH group attached with it. So oxygen will be replaced with NOH group, which is called oxime. Then second reaction suggests when we react it with HCN, then whole HCN molecule will be added. That means addition reaction. So as we can see in this case, here we have CHO group. That means hydrogen will be attached like this and oxygen will have double bond like this. So this HCN molecule will attach with it. That means this double bond will break from here, and now carbon needs to form one more bond. So hydrogen will attach with oxygen from the HCN and cyanide will attach with direct carbon. So you will get CH and CN and OH will be attached with center carbon. So CH, CN, OH. And this second reaction is also possible if carbonyl group is present. Fourth point, glucose gets oxidized to 6 carbon carboxylic acid gluconic acid on reduction with the mild oxidizing agent like bromine water. Now keep in mind, mild oxidizing agents are able to oxidize aldehyde into carboxylic groups. So if aldehyde is present, then with the help of mild oxidizing agent you can get a carboxylic acid compound, and same thing is going on here. So this indicates that the carbonyl group present in the glucose is aldehyde. So reaction is mentioned here. CHO will convert in COOH. So we know that aldehyde groups or carboxylic groups are always present on first carbon. So we can start our structure with CHO as the structure mentioned here suggests. Acetylation of glucose with acetic anhydride gives glucose pentaacetate, which confirms that the presence of 5 OH groups. Since it exists as a stable compound, 5 OH group should be attached to different carbon atoms. Now reaction is when compound having OH group reacts with acetic anhydride COOCH3. That means whole CH3COO group will be attached or it will replace OH group. Now if a compound is stable, then it suggests one single carbon do not contain two OH group. Otherwise, this type of large group will try to attach with same carbon and it will make compound unstable. So here, as mentioned, we have stable compound. That means all the 5 OH groups are attached with different carbons. So we can rewrite the structure like this. So up to this point, as the first point suggests, we have 6 carbons, 12 hydrogens and 6 oxygens. From the second step, we got to know that all of these 6 carbons are attached in straight chain like this. From the next step, we got to know that we have one C double bond O group in this case. If it is ketone, then it will be between, and if it is aldehyde, then it will be at the end. So we are not sure, so let's not put it in this step. From the next step, we got to know that when we use Br2 like mild oxidizing agent, we can actually oxidize our compound into carboxylic acid. So it suggests that this C double bond O group is actually aldehyde group, that means CHO. So obviously this CHO group will be present at the end. So we can add this CHO group at the starting of the chain. Now with acetic anhydride, this compound gives pentacetate compound, which suggests we have 5 OH group, because acetic anhydride will replace OH group with CH2COO group. Okay, so if you get 5 acetate compound or 5 acetate substitutions, then it means it must contain 5 OH group. If compound is stable, then all of these 5 OH group will be present on separate carbons. Now already first carbon is occupied with CHO group and we only have 5 carbons left. So we can predict that all of these 5 OH groups are attached with each remaining carbon like this. Okay, so this is our structure up to this point. Now sixth point is on oxidation with nitric acid, glucose as well as gluconic acid both yields dicarboxylic acid, saccharic acid. So in this case we can say that when we have mild oxidizing agent, then you can convert aldehyde into carboxylic acid. But to convert alcoholic group, primary alcoholic group into carboxylic acid, you need stronger oxidizing agent. So as this reaction suggests, when we oxidize using strong oxidizing agent, you will get dicarboxylic acid compound. Now we already know that one of the compound is already aldehyde. So second compound must be primary alcoholic group. Otherwise, it will be oxidized using Br2. But in Br2 reaction, you only get one carboxylic acid group. But using strong oxidizing agent, you will get dicarboxylic acidic group, saccharic acid. So as these two reactions suggest, in first step we have CHO and CH2OH, and you will get on oxidation you will get saccharic acid. That means both CHO and CH2OH primary alcoholic group will be oxidized into carboxylic acid group. So it suggests one of the OH group will be primary alcoholic in nature. So that means from this point we can say that primary alcoholic group will be present at the end, and to obtain this primary alcoholic group we have to place 2 hydrogens with last carbon. Okay, so it will be something like this. So this is our primary alcoholic group. On oxidation reaction with stronger oxidizing agent, these primary alcoholic as well as this aldehydic group will be converted into COOH group. Now all of these 4 carbon present at the center requires 1 hydrogen to complete their valencies. So let us put 1 hydrogen with each. So this is our basic structure of glucose. It starts with CHO and then we have CHOH, CHOH, CHOH 4 times, and then at the last we have primary alcoholic group CH2OH. So in center we have secondary alcoholic groups, 4 secondary alcoholic groups and 1 aldehydic group and 1 primary alcoholic group. The exact spatial arrangement of different OH groups was given by Fischer after studying many other properties. Its configuration is correctly represented as first. So first structure represents configuration of glucose in space. That means, as we can see here, one of the OH group is present on left hand side and all of the remaining OH groups are present on right hand side for chiral carbons. We are talking about chiral carbons only because these two carbons are not chiral carbon. So they are two-dimensional shapes, or either they have same type of hydrogen, that means they are comparatively symmetrical. Whereas these center four carbons are chiral carbons. They contain four different type of attachments. All of the carbon contains four different type of attachments. So gluconic acid is represented as one will be replaced. Aldehyde group will be converted into carboxylic acid and remaining structure will be same. And saccharic acid, that means both primary alcohol and aldehyde group will be converted into carboxylic acidic group as follow. Okay, so these are the spatial arrangement of the groups in these three examples: glucose, then gluconic acid and saccharic acid.